So now we know how to take derivatives, and we know how to take antiderivatives. When you take a derivative, you're finding a new function from an old one. When you take an antiderivative, you're essentially finding the old function from the new one. If we're asked to take the derivative of a function like big F of x equals 2x cubed, then we have to take the derivative of both sides of the equation f of x equals 2x cubed. We know the derivative of 2x cubed is just 6x squared. But what if we're given the function f of x equals 6x squared, and we're asked to find the integral of f of x, or the antiderivative? Then, as before, we need to take the integral of both sides of the equation f of x equals 6x squared. Well, we know now how to take the integral of something like 6x squared. The antiderivative of x squared is x cubed over 3. This simplifies to 2x cubed, which is exactly what we started with. When we took the derivative of 2x cubed, we got 6x squared. And when we took the antiderivative of 6x squared, we got 2x cubed. This is exactly what you would expect. Of course, we can't forget the plus c, because the antiderivative of 6x squared is 2x cubed plus any constant. If I took the derivative now of this expression, it wouldn't matter what c was, as long as it's a constant, because when I take the derivative of a constant, I'm going to get 0. Okay, so that's a little reminder of what it means to take an antiderivative. Let's look now at a reminder of what some specific derivatives are, and then we'll talk about why we might want to take an antiderivative in that particular situation. In differential calculus, we learned that the position function of a particle or some other object is often given by s of t. Here, s of t is equal to negative 15 halves t squared plus 88t. This just tells us how far the particle has traveled after t seconds. T is the number of seconds, and s is the total distance at that number of seconds. So, for example, if we wanted to know how far the particle had traveled after 3 seconds, we would simply replace the t with 3. After 3 seconds, the particle has traveled a total distance of 196.5 units. We also learned, though, that the velocity of such a particle is simply the derivative of the position function. The derivative of negative 15 halves t squared plus 88 is negative 15 halves times the derivative of t squared plus the derivative of 88t. This simplifies to negative 15t plus 88. If we want to know how fast the particle is going at 3 seconds, we plug 3 into the velocity function. The particle is traveling at 43 units per second, 3 seconds after it starts. Also recall that the acceleration function is just the second derivative of the position function, or the first derivative of the velocity function. Here we're just going to get that acceleration is negative 15, no matter how far into the process we are. What happens, though, if what you know is the velocity function and what you're looking for is the position function? Well, since velocity is the derivative of position, position is the antiderivative of velocity. So at first glance, it looks quite simple. But there's going to be some additional information that we need to really solve a problem like this. Let's go ahead and start with this velocity function and see if we can find the position function from it. If the velocity function is just the derivative of the position function, then we should be able to find the position function, s of t, by integrating the velocity function. Here, since I'm anti-differentiating with respect to the variable t, I'm going to write dt, not dx. Because we actually know the function, I can write the integral of negative 15t plus 88 dt. We have some properties that let us do problems like this now, so let's go ahead and rewrite this as negative 15 times the integral of t dt plus the integral of 88 dt. This is going to be negative 15. The integral of t is just t squared over 2 plus the derivative of 88 is 88t. And of course, I must remember my plus c. I can rewrite this as negative 15 halves t squared plus 88t plus c. You probably recognize this function as the one we started this section with. The position function we were given to differentiate was negative 15 halves t squared plus 88t. We didn't have a plus c there. If I want to know exactly what the position function of this particle is, not just the family of functions that it comes from, then I have some more work to do, and in order to do that, I need some more information. What I need to know is the particular position of the particle at a specific point in time. The easiest point in time to work with is t equals 0. And oftentimes you'll see a problem written like this where you're given v of t, you're asked to find s of t, but then you're also told that s of 0, when t equals 0, is equal to some number. Let's say in this case we're told that s of 0 is 22. What this means is that since now we know the position function but with the plus c in it, but we also know that s of 0 is 22, we can rewrite this position function with a 0 in place. So instead of this position function, I would have s of 0 equals negative 15 halves times 0 squared plus 88 times 0 plus c. That's s of 0. That's the position function when t equals 0. But I'm also told that s of 0 equals 22. So I can take this position function and set it equal to 22. Now, when I do the algebra here, or really the arithmetic, what I get is that s of 0 is equal to 0 plus 0 plus c, and that is equal to 22. So now I know that c is equal to 22, and I can replace that in my position function. So my actual position function, s of t, is equal to negative 15 halves t squared plus 88t plus 22. This is called an initial value problem because in addition to finding the position function from the velocity function, I'm given an initial value, the position that the particle is in at time 0. With that additional information, I can find the actual position function of the particle. That's the general idea behind an initial value problem. I'd like to do one more because there's actually a whole nother level we can go to with a problem like this. In this particular example, I was given the velocity function and asked to find the position function and then told what the initial position was. But what if I'm given the acceleration function and asked to find the position? In that case, I'll need to find the antiderivative of acceleration to find velocity and the antiderivative of velocity to find position. In addition to that, I'll need to be told what the initial position is, but I'll also need to be told what the initial velocity is if I'm going to find the exact specific position function of my particle. Let's go ahead and get started with an acceleration function. This is a typical initial value problem. You're given an acceleration function, and you're also given an initial velocity and an initial position. and we're asked to find the position function of the particle. We're starting with an acceleration function. So the first thing to do is to take the antiderivative of the acceleration function to find the velocity function. The antiderivative, or the integral of a of t, is the integral of the function, which is negative 24t plus 6. We know how to do these. Bring the constant out front, take the integral of just t, and take the integral of just 6. And in fact, I could have brought this 6 out front as well and thought of this as 6 times the integral of x to the 0 power. This gives me negative 24 times the integral of t, but the integral of t is t squared over 2. The integral of 6 is 6t. So there's my antiderivative, but I need a plus c. And I can tidy it up. Negative 24 over 2 is 12, negative 12. So I have negative 12 t squared plus 6t plus c. There's the family of antiderivatives, the family that gives me the velocity function for the particle. The problem is this is a whole family of functions, and I want the one for this particular case, this particular particle. The good news is that I'm told that the initial velocity of the particle is negative 1. In other words, at t equals 0, the velocity is negative 1. I now know v of t, so let's find v of 0. It's what you get when you plug 0 in place of t. But v of 0 is equal to negative 1. Therefore, c must be negative 1. With that information, I can go back to my velocity function and replace the c with negative 1. I'll write this new function off to the side and then erase the screen so I can do the next part, which is to find the position function. The derivative of the position function is the velocity function, and the derivative of the velocity function is the acceleration function. We were given the acceleration function, and we took its antiderivative, we took its integral to find the velocity function. Now what we're going to do is take the antiderivative, or the integral of the velocity function, to find the position function. In order to do this, remember we need these initial conditions. When we took the antiderivative of the acceleration function to find the velocity function, we had to use what we knew about the velocity at time 0 in order to complete the process. We'll need to do the same thing with the position function. For now, let's start by taking the antiderivative of velocity to find the position function. Since we have v of t equals negative 12t squared plus 6t minus 1, we can say that the position function is equal to the integral of negative 12t squared plus 6t minus 1 dt. Remember, the t here is instead of the x because our variable is a t instead of an x. Now, using the properties that I know about integrals, I can rewrite this as negative 12 times the integral of t squared dt plus 6 times the integral of t dt minus 1 times the integral of t to the 0 dt. That's going to give me negative 12 times the integral of t squared is t cubed over 3 plus 6 times the integral of t is t squared over 2 minus 1 times the integral of t to the 0 is t to the 1 over 1. And of course, when I'm finished, I'll have plus c. Cleaning things up, I get negative 12 over 3, which is negative 4 t cubed. 6 over 2 is 3 t squared. Negative 1 over 1 is just minus 1 times t to the power of 1 is just t plus c. So this is at least one of the position functions. The problem is it's actually a family of functions because c can be any constant, and I want to know the specific position function for this particle. The nice thing is I've also been given some information about the initial position of the particle. In other words, now that I have a position function in general, I can use the fact that s of 0 is 0 to find out what c is in this case. S of 0, I'm told, is equal to 0. But I also know that my position function, s of t, is negative 4 times t cubed plus 3 times t squared minus t plus c. And wherever I had a t, I can replace that with 0. This gives me the idea that 0 is equal to 0 plus 0 plus 0 plus c. So in this case, c really is 0. Where before I had my position function written as a family of functions, I can now take this version of the function and rewrite it with the now known value for c. It turns out that c is 0, so this is going to be plus 0, which of course I don't actually need to write. I'll put my position function here. S of t equals negative 4t cubed plus 3t squared minus t. I can write plus 0, but I certainly don't need to. The thing to be aware of is that in this case, I know c is 0. I haven't forgotten to write plus c. I've actually calculated what c is, and it happens to be 0. A minute ago, I did a problem for you where we started with velocity function and I asked you to find the position function. This time, we started with the acceleration function, and we found the position function from that. The process is the same, but in the first problem, I only had to work through that process once. In the second problem, I had to work through it twice, because the position function is the second antiderivative of acceleration, whereas the position function is only the first antiderivative of velocity. Okay, I think it's time for you to try one. Here's yours. If I give you the velocity function, v of t equals 6t squared plus 7, find the position function, s of t, of the particle with that velocity function. Specifically, find the unique position function given that the particle at time 0 is at position 7. In other words, at t equals 0, the answer should be 7. How did you do? Did you remember that the position function was the integral of the velocity function? That's just the integral of the function we were given. We were told what the velocity function was. Don't forget the dt here. That's important. I can rewrite this as 6 times the integral of t squared dt plus the integral of 7 dt, or if you prefer, 7 times the integral of x to the 0 dt. Six times the integral of t squared is 6 times, well, the integral of t squared is t cubed over 3. And the integral of 7 is 7 times the integral of x to the 0. So it's x to the 1 over 1. Finally, 6 over 3 is 2, so I have 2t cubed plus 7x plus c. If this were an exam problem, that would probably get you some partial credit. The problem is, this is a very particular kind of application. We're not quite finished yet. It's important to take this to the next step by noticing that we are given s of 0 equals 7. That tells us that the position function, s of t, which is 2t cubed plus 7t plus c, should equal 7 when t is 0. So if I replace t with 0, I get 7. 0 plus 0 plus c equals 7. So now I know what c is. And now that I know what c is, I can plug it back in to my position function. My particular position function is s of t equals 2t cubed plus 7t plus 7. I've just noticed that back here I used an x instead of a t, so let me make that correction. Same thing here, and I think those are the only places where I did that. It's important to be consistent with your variables. It's just human nature to make mistakes like this, but do be careful and make those corrections when you catch them. At any rate, here is my position function, right down to my plus c, with the specific plus c that I needed for this particular position function, for this particular situation. Is that what you got? That's it for this video. In the next video, we'll be using integration to approximate areas. See you there.